Okie dokie. Let me make sure nobody's in the waiting room. All right, so let's pick up where we left off last time. Homework for last class was to finish our writing of our, is that in here? Connecting all of our rooms and exits together. So last time we'll just review it here in the slides first. You know, we decided we wanted to create a map that looked like this, where it's kind of a mimic of the computer science department, where we have this entrance and then we have a whole bunch of these room objects and they're linked together through exits. So we started building this out. I think we built just this main entrance area. So as we come down through here, we defined all of our rooms here for the board. So we have 14 total rooms. And then we started adding exits to room 7. So room 7 had a south, east, and west. And this was room 7 right here. So we gave it a south exit to entrance, a west exit to hallway, and an east exit to hallway. That was the room 6. So room 1, room 6, room 8. So we put in those exits. So we made all the rooms exist first so that all these guys already existed. And then we went back through and started putting in the exits so that they can link rooms that already existed. So let's go. So your homework for today was to kind of finish doing that linking. So let's do that real quick here. So we'll just go in order. So room 1 is going to have an exit to the north to room 7. So R1.add exit north R7. Room 2 will have a exit to the east to 3 and north to 5. East to R2. And north to R5. And here I'm just going to actually...
I think east to R3.
Oh, is it? Thank you. Thank you. All right, and then room 3 is west to R2. And then room 4 is west to R5. Okay. Then room 5 is south to 2, east to 4. Let's just start with that. South to 2, east to 4. R4, north to 10, west to 6. Okay, then R6 is going to have east to 5, west to 7. Okay. R7 we already have in there. R8 should be east to 7, west to 9, north to 12, east to 7, west to 9. R7. West to R9. And then north to R12. Right, then R9. We'll just have east to R8. All right, then R10, we'll have south to R5. R5, already got that. All right, R11, we'll have west to R12. R12, we'll have east to R11. South to R8. West to 13, north to 14. $14. 13, we'll have east to 12. And 14, we'll have south to 12. All right, so that should be our complete map. Let me get rid of this extra crap down here. All right, then we created an inhabitant. And we put them into, well, we put them into room 7 initially, but if I put them into room 1, then I tell 1 to display itself, and then we run this, we see that we have the entrance with an exit to the north leading to hallway. Also here was Mike, the inhabitant that is in that room. Okay, so I think that was the homework assignment. So any questions about what we just did there? Okay, so then the next thing we'd like to do is we want to be able to allow our inhabitant to walk through this, this world. All right, so if we go back here, we have our inhabitant in this room, but we'd like for them to be given an option showing the current exits. Maybe you have an exit to the north. You have, there's only one exit to the north. They should be able to say, oh, I want to travel to the north, and they get removed from this room and put into this room. And then they see that this room has 3 exits to the south, to the east, and to the west. They should then be able to choose to go to the west, choose to go to the west, choose to go to the east, to the north. They should be able to walk around an apartment where they get removed from one room and added to another room and shown what their current surroundings look like. All right, so we want to create an interactive program that will prompt the user over and over again for this type of thing. Okay. So let's start with just that part of it. So we have our inhabitant. We went ahead and added them to the first room, and then we want to start asking them stuff. All right. So what we'll maybe do is we'll say we could put them in an infinite loop here if we wanted to, and just say, look, forever, we're going to keep asking you questions. So we're going to say, what direction do you want to go? Something like that. We'll read in that direction. Now, as of right now, notice here that we have our rooms and we have our exits. So this is the exit leading. So these are going to be the choices they're going to be choosing from: north, south, east, west. In this case, we only have a single exit to the north. So they should be entering in a direction that exists. Now, if you remember, when we added this inhabitant to the room, when we said r1.add inhabitant, the inhabitant, let's go and look at our room object. We also let the inhabitant know about the current room they're in. So here's add inhabitant for a room. It takes the inhabitant we're adding to the room, and it sets the room's current inhabitant to that person, but then also sets that current inhabitant's current room equal to this room. So if we go back to our picture here, this room right here knows that it has this inhabitant, but this inhabitant also knows that he is in this room. Both of those things occur. That's what those 2 lines of code do. The first line says we would let this guy know that this inhabitant is now inside. The second line of code lets this inhabitant know that his current room is this room. So this lets the inhabitant know that his current room is the room he's currently in. That way an inhabitant can look at his room. And where that's going to come into play here is, instead of just us randomly saying, well, we're just going to assume he's in room R1 and telling that to display itself, we're instead going to say we want the inhabitant current room to display. The inhabitant is in a room. Whatever their current room is, we want that room to display itself so we can see what room they're in. All right, so let's just see what this looks like right now. So initially we put them into room 1. We run this and we see that they are in the entrance. So now we're getting to it, this line right here, the inhabitant.currentRoom.display. This is showing the room they're currently in. All right, so now when we're going to read in a direction, so we're saying what direction do we want to go? I'm going to put in north, but we're not actually doing anything with that yet. So when I type in north here, I'm going to read it in, and I ultimately want to remove them from the current room and take the exit to the north. Okay, but we're not actually doing that logic yet, so it's just going to show us our current room again and ask us what we want to do because we're in a loop that runs forever. So this loop just says forever, while true, just keep doing this stuff over and over again. We'll put in some logic here eventually that lets us break out of this loop. But for right now, we're just going to keep asking them what do they want to do and let them walk through our the maze. All right. So now we need to give that ability to walk through that maze. The way we get between places is through an exit. So remember, an exit has a direction, and then it has a destination room, a place that it leads to. So when we are in a room and we take an exit to a direction, we need to first, so if we think about this in our picture, if I want to take this exit to the north, I first need to have the current room I'm in remove me from that room. So I'm no longer in that room. Then it needs to teleport me through that exit to that exit's destination and add me to that room. Okay, those are the two steps. Otherwise, I'll be left with a situation where I'll be in this room as well as this room. So room 1 will think it has me as an inhabitant. Room 7 will think it has me as an inhabitant. I will think I'm in room 7 because that's the last room I was added to. So I set my current room to room 7, and now we've effectively cloned ourselves. Even though it's just one pointer, it's the same object, the same memory address that lives in both of these rooms. So in order to do these steps correctly, and this is where drawing pictures comes in handy, is I want to first, if I'm going to take this exit to this room, I'm going to first ask the current room I'm in to remove me. So I'm no longer linked to this room. Then I'll ask that exit to teleport me into the next room. So I'll ask the room it leads to add me to it. All right, so we already have that part. We already know how to add ourselves to a room. So now we just need to, when we take an exit, we need to remove ourselves from a room first. Then we can take the exit. Or whether we do it first or last, we'll see how it ends up panning out. But we definitely need to get ourselves out of this room before we can add ourselves to another room. All right, so let's look at this this logic. So we got to decide who's going to do the work. If we ask an exit to allow a person or an inhabitant to take the exit, we can add that function in here. And do we have enough information? Well, if we give an exit an inhabitant, we can add that inhabitant to the destination room. So maybe we do something like def take exit, and this guy will take the inhabitant that's taking the exit, as well as the current room, and, well, we don't need the destination room. We already have the destination room. So we want to know, actually, I don't even need to know the current room. I just need to take in an inhabitant. So the inhabitant is going to take this exit. Now, ultimately, what we want to do is we want to set destination room, self.destination room. And we want, let me stop my program, otherwise it's going to keep putting me down there. And we want to add inhabitant to that destination room. Which inhabitant? Our inhabitant. This guy. So that's ultimately what we want to have happen. We want to add this inhabitant to our destination room, which we already saw that add inhabitant also lets the inhabitant know about the room they were just added to. But before I can do that, I need to remove the current person from the room he's currently in. So we know the room this inhabitant is currently in is inhabitant dot current room. That's the room the inhabitant is currently in. we now need to remove that guy from the current room. Let's see, what do we call it in here? We just have a current inhabitant. So what I'm going to do is for a room, I'm going to say def remove inhabitant. Now I'm writing it this way, even though right now rooms only have single inhabitants. Well, you know what? Let's not think ahead too much. So we can actually do it this way then. I'm going to say remove inhabitant, and this guy will just say self dot current inhabitant is equal to none. So he forgets about who's in the room. That's what remove inhabitant will do. Eventually, what we're going to have is we're going to have a list of inhabitants that are in a room. So when we say we want to remove an inhabitant, we probably need to take in the inhabitant we want to remove, because it's going to be one of 3 or 4, inhabitants that are currently in that that room. But right now, a room can only hold a single inhabitant. So we'll go ahead and let that single inhabitant just get removed. And to do that, we just tell the room to set their current inhabitant to nothing, which effectively says, forget about who's in there. All right. So we've added.
When does that come into play? Does it just do that automatically? Or like after you say you want to go north or west or east?
Yeah, you're going to see how it plays out here in a second. So as far as what we just did right here, just think about we've given a room object the ability to remove their inhabitant. We haven't called upon that ability yet, but we've given him that ability. So I could point at a room and say, forget who is in you. Forget the person that's in your room. That's the ability I've given right now. So we'll go back down to exit now, and we'll use this ability. So when we take an exit, we'll ask the inhabitant's current room to remove. Actually, did I have it taken the inhabitant? I think I did not.
It's just dot remove.
So like this. So the inhabitant will ask his current room to remove himself from it. That's what we're doing here. When we take an exit, we'll ask it's the inhabitant taking the exit. So the very first thing is we're going to ask the inhabitant to look up his current room. So that's this guy. This is the inhabitant. The current room he's in is this guy. And then we'll tell that room to remove their inhabitant, which effectively will be that. This room now no longer thinks it has an inhabitant in it. Then the very next line, we're going to get to our destination room, which that's where we're currently, if we took the exit to the north here, this guy, the destination room is this guy. So we're going to ask him to add this inhabitant to him, which also then lets the inhabitant know about the current room he's in. So that's the 1-2 punch here. Make the current room forget about you, then add yourself to the next room, the destination room. So again, all we've done here is we've given exits the ability to the ability to have an inhabitant take an exit. We haven't called upon this yet. All right, so now we go back to our map here. If we imagine that we're currently standing in this room and we see that, oh, there's an exit to the north, and it asks us what direction do we want to go. When we say, I want to go to the north, what we'll have to do is this room will have to look up from its list of exits. In this case, he only has 1 exit, but if I was in this room, I'd have 3 exits to choose from. He'd have to look up through his list of exits, the exit with a direction to the north. And he would then find this exit. He can then have that exit, have the inhabitant call take exit on that exit. So let's write that. So we're going to add an ability to a room to search through their list of exits for an exit that has a direction equal to whatever the person entered in. So we'll go to room. And let's go ahead and say, we're going to define something called find exit. We're going to give it a direction. Now remember, a room has a list of exits that presumably has been filled in with some exits. Where did we add those exits? That was what the homework assignment was for today, where we added a whole bunch of exits to rooms. So now our rooms have some exits in them. So if I want to find a particular exit in that room, that is an exit that has a direction. So here's our exits. Exits have a direction that they go. I want to find the room that has a direction equal to the direction the person has typed in. So the function we're writing right here in find exit will look through the list of exits, looking for the exit whose direction is equal to this. So for an exit in self.list of exits, if an exit dot direction is equal to the direction you typed in, then we'll go ahead and return that exit that we found. All right. So that's what find exit will do. I give it a direction. It'll look through this particular room's list of exits and return for me the exit that is associated with that direction. Now, since it's possible, let's just say that in my map right here, I'm in this room and I try to take a exit to up, let's say. Well, then I would get, I mean, it's not going to find an exit with a direction to up. I only have a direction to the north here. So we can assume for right now that the person who's navigating the map only gives us directions that we're allowed to go. But we could do some error checking in here where, hey, it might give us nothing. You know, if it doesn't find an exit with that direction associated with it, it might return none. I didn't find that exit. You know, try again, something like that. So just for the sake of completeness, go ahead.
Is there a way, like within this function, that we can force the direction to be all lowercase when they type in their input?
Yep.
So that we don't end up with an error if you like do capital N for north instead of the lowercase?
Let's see.
I think it's dot lower or something like that, right?
It's like a string thing.
Yeah.
Python string to lowercase. Looks like it's just lower. And we can test that real quick. I can say hello dot lower, and that gives me hello. So what we can do here is we can say direction is equal to direction dot lower, and that guarantees it's in all lowercase. Now, at the same time, though, we need to then make sure that the direction we're comparing it to is also in lowercase. So really, maybe we want to do this. Dot lower like that, and dot lower like that. So when we're looking at an exit, we'll look at the lowercase version of its direction and compare it to the lowercase version of the direction that was entered in. And that'll have it compare it all in lowercase, just in case somebody types in north with a capital N, like you said. Okay, so that's how we can find an exit, and it'll return the exit for us. And then what I'm going to suggest we do is we return none in the event that we never get into this if statement. So if we happen to look for the exit, we never find it, we'll just return none. We're not necessarily going to use that value right now. That's like if the person tries to take an exit that doesn't exist. I'm just kind of writing logic that is complete here. Most modern programming languages, most strongly typed compiled programming languages like you'll run into next semester when we deal with Java, they would not let you write this function without that return statement in there. Because in Java, we have to define that a function returns something. So we would say, oh, well, this guy is going to return an exit. We would define that his return type is going to be an exit. And the fact that we have defined what it's going to return, we are now forced to return something. So, but in this case, we only conditionally return something. That's only if we get into that if statement. There's no guarantee we actually ever get into that if statement. We might look through our entire list of exits and never find an exit whose direction is equal to the direction it was passed in. Therefore, this function would never return anything. So in Java, the compiler would be complaining to us that says this function must return a value, even though we didn't. Python's okay with that because a function will just boil down to none on its own if you don't return anything. So the good programming practice version of this would be to say, well, if my function couldn't do its job normally, I'm going to go ahead and take it upon myself to return nothing, even though I happen to know that it'll boil down to nothing if I don't do anything otherwise. So this is being explicit about this, that look, I checked all my exits. I didn't find anything that matches what you were looking for. So I ran out of my for loop. I'm sitting right here. That means I didn't find that exit. So here's nothing. But at least we explicitly return nothing, which will be compatible with future languages you use that hold you accountable for what you advertise the return type to be. So I would call this good programming practice, where this would be considered poor programming practice, even though it's acceptable in Python. Python will let you get away with it. All right, so now we have the ability to ask a room. So really try to focus on this idea of what are we doing in this scenario. We're teaching each of our individual objects different abilities that we're then going to use in conjunction with each other to solve our problem. All right, so now we've taught a room to find an exit. We taught an exit to take an exit with an inhabitant. So once we find the exit we want to take, we can ask that exit to take an exit, and we can pass ourselves to that exit. It will take us out of our current room and put us into the new room. So then down here in our loop, after we've read in our direction, we would say the exit is equal to the inhabitant dot current room dot find exit to that direction. So we're going to ask the inhabitant for their current room, the room they're currently standing in. We'll then ask that room to find their exit with this direction. So if I'm currently in this room, this is the inhabitant, their current room is this guy. We ask this guy to find his exit with, in this case, let's say we typed in north. It would then search through his list of exits, which only has one exit in it. It would find this exit that has north in it, and he would return that value into this variable called the exit. Once we have that exit, we can say if the exit is equal to none. If we want to do a little error checking here, we can print out direction does not exist in this room. So give them a little error message type thing. Else, the exit must be a real exit. So we'll go ahead and take that exit. So we'll say the exit dot take exit. And we have to give this guy the inhabitant and the direction. If we go up to our exit object and we look at how take exit works. Oh, we don't actually need to give it the direction because it already has the destination. So we actually got the direction already up here. When we searched for the exit with this direction, we got an actual exit. So we no longer need to use the direction anymore. Now we have the correct exit that's leading in the correct direction. We'll just pass ourselves to that and say, we want to take this exit. And what will that guy do? He'll remove us from our current room, and then he'll add us to the new room. And then this loop will spin back up and will show the inhabitant's current room. So this loop right here should allow us to walk throughout the entire department now. Each time through, what do? We display our current room. We ask, where do we want to go? We search for the exit in that direction. Then, as long as it existed, we'll take that exit, which will remove us from the current room, put us into a new room, setting our current room to that new room. So that the next time through the loop, we will display our new room. So let's go ahead and do this. So here we're in the entrance. We see an exit to the north. I'll type in north. Now notice we're in the hallway, which is correct, right? Now we're in this hallway. We should see an exit to the south, to the east, and to the west. So we have a south and the east and to the west. So let's go to the east, baby. Still in the hallway. We'll go to the east again. Still in the hallway, but now we're at the end of the hallway where we can go to the east of the Mac lab. So now we're right here. We can go to the east of the Mac lab. We can go south of the soda room. We can go north of this room, or we can go back to the west. So let's go south. And then here we can go back to the north, and we can go to the east to our security sandbox. There's east. So now we're in the security sandbox, only one exit back out of here to the west. So right now we're standing in this room right here. So we can go to the west and then the north, we're in S118B. So there's west, north. Notice it says direction not does not exist. That was my error checking. So we'll go to the north and then go to the north again. And now we're in S118B. So now let's head down to this other side and let's get to the laser cutters. So we'll go to the south to get back into the hallway. Then we'll go to the west, the west, the west, the north, and then the north. And now we're in by the laser cutters. So now we're sitting in this room. All right, so now we have the ability to have our inhabitant walk around this map. And how did we pull that off? We gave our individual objects different abilities that we imagined from this picture. We said, okay, if I'm standing in this room and somebody asked me what exit do I want to take, I'm going to say I want to go to the north. So I'm going to ask this room to give me the exit leading to the north. Then I'm going to call that exit's take exit with myself, which will remove me from this room and put me in that exit's destination room. And then we just keep doing that over and over again. It shows me the exits for this room. If I want to go to the east, it'll give me this exit. I will take that exit, which will remove me from that room and put me in that destination room. So do you see how what we've done here is we've given our objects some abilities, and those abilities in and of themselves might not do that much. You know, when we say, find this exit from this room, we might say, well, okay, that's interesting enough, but what am I going to use that exit for? So all we did is we wrote into a room to find an exit, and it gives us an exit. Now it's up to us to do something with that exit. Okay, so now I've decided, okay, now that I have an exit, what can I do with an exit? Well, we could take an exit, take exits, take us as a parameter, removes us from our current room and puts us into a destination room. That's what that little ability did. So we wrote these little tiny abilities into these different objects, and we use them in conjunction with each other to actually accomplish some tasks. And that's where drawing this picture comes in handy. All right, because now we can visualize the things that we're doing. This is an inhabitant, this is a room, this is an exit. And all these things work together to kind of build this map. And now we're also traversing this map and walking around. Okay, so questions about any of that yet? And then what I could do here is, I think I gotta move this out of the way.
You paste your inhabitant class into the chat for me, please?
I'm putting it onto Slack. Is that good?
Okay, yeah.
So there's the entire program right now. I just put onto Slack. Okay, so now we have our map and we have the ability to walk through it. What do we want to be able to do next? Okay, we're the developers. We're creating this quote virtual world, let's say. So what do we think would be cool to be able to do next?
Teleport?
Well, so what do you mean by teleport? Like get from one room all the way to another room?
I mean, I guess. Like select R14 and just teleport from R1 to R14.
Okay, and why would that be useful for us now when we can walk there?
Shortcut.
Yeah, well, I guess I want to think about this like kind of like a video game we're building. So we have our room, we could walk through this room. What's missing from a video game perspective?
NPCs.
Yeah, enemies, things to kill, right? Okay, so we, because of course that's what happens in the computer science department is there's just death.
Laser room boss or something.
That's right. So we're gonna put some other, because I've mentioned a couple of times that we're gonna have like a list of inhabitants in a room, right? So if we kind of think about that, right now we have this concept. Let's see, I'm gonna go down to
Dr. Lippman.
Yep.
The NPC could technically be used just under as the inhabitant as well, right?
yes,
it's
but
just
what
a
if we
separate
want to?
inhabit-
What if we want to occupy the same room as a NPC? Let's say there's a rabbit in the department, and we want to be in the same room as the rabbit. That way, we can attack the rabbit. Something along those lines. So that means
that'd be
we
cool.
need to retrain a room so that a room can hold a list of inhabitants, right? So what we're going to do here is we're going to start talking about, this is another skill in object-oriented programming, and that is the skill of inheritance. So we're going to say we have this generic inhabitant. Right now, we are an inhabitant that just walks through the world and all we have is a name. So there's nothing really special about us right now. But we're going to start off with this idea of a generic inhabitant. And then from that, we're going to create a player. And we're also going to create an NPC, a non-player character. All right. So we're going to have a top level class that is called inhabitant. And from that, we are going to inherit other classes. And I think I have some examples of that in here. So just looking at some example code here for this, let's assume that we have a generic class called automobile. So automobile would be kind of like our inhabitant here. Okay, so when you go out and you buy a car, even though all those cars on the lot are all automobiles, you don't buy a generic automobile. You buy a car or a truck or a motorcycle. And then even within a car, you buy a 4-door sedan. And then even within that, you might have like, categories of sports car versus, whatever, that kind of stuff. All right. So in real life, we kind of have this idea of an abstract thing. Okay. So for instance, if you walk up to somebody, I've used the idea of a smartphone pretty often. Okay. When you ask somebody, do you have a smartphone? Now we just assume everybody does, right? They say yes. Then you ask them what kind. So now you're expecting them to give you an answer kind of like either Android or iPhone. And then within Android, you might be interested in, oh, which Android phone? With an iPhone, which iPhone? That type of thing. So we further classify things from their most generic. So what we want to have inside of our world here is we want to have a bunch of inhabitants, but we want there to never actually be a generic inhabitant. We want the inhabitants to be either players or NPCs, for example. All right, so we're going to create, well, we already have our inhabitant class. And then what we're going to do is we are going to create some additional classes that are built in terms of that inhabitant. So you see here that we have automobile, and all automobile has is a number of wheels in this example, and then they can display themselves. And then we're going to have a car, and a car is an automobile. So instead of it being built in terms of a generic object, because there's this invisible thing up here, I'll show it to you over here. When I created an object here, room is built, I think it's a lowercase o, and yeah. Room here is built in terms of something that is a generic object. All right, and generic objects don't really do anything from our perspective, but they do exist so that we can start building our own custom objects. So if we don't put anything in here, an object is automatically built in terms of the generic object. All right, so that's what's kind of hidden right here that we don't see. But now, when I define a car in this example, rather than letting the default hidden object be there, I'm going to go ahead and say, I'm actually building this car in the image of an automobile. So this car is an automobile. He's just going to be kind of a more specialized version of an automobile. And how is he specialized? Well, notice here that we're using, we have our constructor for our car. And inside here, we're actually calling, so the super keyword is used for an object. Here, I'll go ahead and write it. Probably have it in here. Yep. It's how an object refers to its parent from within itself, as opposed to self, which is how an object refers to itself from within itself. So we've already been introduced to the self keyword, which when we're inside of an object and we say self, we're talking about us. Okay, so if I'm an instance of a human, all right, and I say self or myself or me, those are all, let's say, the same thing. I'm talking about myself, this particular instance of human. Okay, where if I was in super, I would be talking about my parent, the super class that I came from. So my mom or my dad. Okay, so inside of a class, self is how we refer to ourselves. Super is how we refer to our parent. So if we're inside of a normal class like we've been building, super would be the instance of object that we are built in terms of. But in this case, super for car is the instance of automobile that this car is based on. So what am I doing here? I'm talking about my parents' constructor, their init function. And the parents' constructor takes in a number of wheels. So what we're doing here is whenever we build a car, we're assuming that all cars have 4 wheels. So we're going to go ahead and just say, well, if I'm building a car, I'll just go ahead and call my parents' constructor and pass it 4 wheels.
Dr. Lippman.
Yep.
If we were to have in the class automobile then, and its instructor to take another instance, like a name of a vehicle, like say BMW, and
Yep.
then we went down to class car, would we just, in that super function, would we pass it the second parameter then to
Yeah.
like 4 comma
Yep, any way you cut.
name?
I'm
Okay.
calling my parents constructor here. So if my parents constructor takes 9 parameters, I have to give it all 9 parameters. Here.
Okay.
Yeah, whatever this guy is expecting, if I want to build myself in terms of my parents, I'm going to do that. Now, usually what we would do is we would then further differentiate ourselves. And now we'll see that in our example here in our program. But just to kind of finish this example here, we have this core automobile, and then we have cars and motorcycles built in terms of automobiles, where they actually just give the, you know, the default number of wheels. So kind of a simple little example. But now I can build cars and bikes, and these guys have the correct number of wheels, even though I never actually built an automobile. Automobiles ended up being the base for cars and motorcycles. So this is something called inheritance in object-oriented programming. No different than what we, that inheritance is in real world. You know, we inherit certain traits from our parents, and then we have some traits that are specific to us that differentiate from what we got from our parents. All right, so we're just modeling. This goes back to this idea of what's the job of a computer programming language? It's to allow us to tell a computer what to do. It's also there to help us solve problems in a way that's similar to the way we already solve problems in real life. Well, in real life, we think, you know, we come from something else. We come from our parents, and we get a lot of stuff from them, but then we further differentiate ourselves from them. So we're our own entity, okay? So the same idea, that same problem solving concept exists in our modern object-oriented programming languages. That doesn't mean we always do something with it. So for instance, up to this point, we've created all these objects like rooms and exits, and we've been perfectly fine just having those guys just come from the generic object, which means the simplest thing that can exist, right? You know, if I think about, you know, in real life, you know, let's say you pick up a paper clip or something like that. A paper clip is built in terms of, well, actually, I guess we could still even use that as an example of inheritance. It's probably built in terms of a base metal that's been bent a certain way, something like that. But you just keep getting more and more generic, and you just decide like, okay, this is a rock. Okay, a rock is built on top of, you know, let's just say, I'm probably skipping some steps here, but let's just say it's built on top of atoms. So in real life, we decide that our base thing for matter is the idea of an atom. All of our things are built up of these little building blocks called atoms. And I know there's subatomic particles and stuff. Just forget about that for right now. Let my example work, okay? So we're gonna say the most basic way things are put together in the world is through atoms, all right? And when we think about objects in the world, they are specialized collections of atoms, all right? So when we have something very simple, we might inherit directly from an atom. Just say, okay, we have a whole bunch of atoms that make up something. But then when we have something more specific, you know, when we have a smartphone, and then we have specific kinds of smartphones that have specific abilities associated with them, we further classify things through inheritance like that in real life. Okay, so questions about inheritance in general, kind of the idea of what we're trying to accomplish with inheritance. All right, so let's apply this then to our program here. So we're going to say that an inhabitant is our base class here. Maybe inhabitants just have names. We'll give a little bit more to them here soon, but for right now, we'll just say they have a name. Now, a player, actually, let's think about this. Because we're ultimately going to want these guys to fight each other, you know, because that's what's going to happen in our game, right? So they're very violent. Okay, so because we want them to fight each other, we're going to have to think about, well, when a player attacks an NPC, so let's say that we have a, you know, it's us versus some monster in the department, and we want them to fight each other. If you think about your modern video games, I know not all of you are necessarily gamers. You know, each one of these guys has some level of life. Sometimes it's called hit points, sometimes it's life force, whatever. They have a measurement that says, how alive are they currently, and how much more damage can they take before they kick the bucket. All right, so we might say that all inhabitants, let's go this route, have a number of hit points. Okay, so that's like their life force, how much they can, how much damage they can take. Now, maybe since we're gonna make this mostly let's say a melee type video game instead of, we could add magic in later, but let's say they also have strength. All right, the stronger you are, the harder you can hit type thing. Okay, now let's also say that they have armor. All right, so if we're going back to like the old Dungeons and Dragons tabletop day, we have hit points, we have a strength, and we have an armor class. And the idea is that when the player is attacking the monster, they're gonna try to hit the monster and see if they can clear their armor. That usually happens through like a dice roll, or rolling a d20 or something. And so they first determine, do I hit the monster? And then they use their strength to determine how hard I hit the monster. That type of thing. So then you have this back and forth until somebody dies. All right, so we kind of create this concept of a death match, if you will. Okay, so in our game here, we want to have a basic inhabitant, where a basic inhabitant has a number of hit points, it has a strength, it has an armor. But then from that, we're going to have players. Maybe a basic inhabitant also has a name. Okay. So now we want to differentiate a player from an NPC. Now, a player from an NPC, maybe we go ahead and I want to kind of create an arbitrary differentiation as well. But in general, players are human controlled. So this guy is going to have interactivity associated with it. It's gonna, as a player, we're controlling the player. Where the concept for this NPC is the NPC, it does things on their own. All right. So what we might say is for an NPC is either, let's say, maybe they have something called whether they're hostile or not, true or false, hostile. Okay, so a hostile NPC would automatically attack you when you enter the room, whereas a non-hostile NPC would sit there and mind its own business unless you attacked it. All right, so let's just say that a NPC is hostile or not hostile, whereas a player is completely interactive, where we get to decide how hostile we are, and that's not something we keep track of. Okay, so we want to create this inhabitant class where we have hit points, strength, armor, and a name. And maybe we also have a differentiation depending on our NPC. We have a higher max strength or a higher max armor or higher hit points, whatever. Because usually in our video games, our heroes, the guy that the player is controlling is usually kind of stronger than the average Joe in the game. So we're going to try to represent that through this inheritance model. All right, so we're going to go and update our inhabitants now so that they have hit point, strength, armor, and a name. So we'll get to our inhabitant. So right now, an inhabitant has a name. They also have a current room, so we definitely want to keep that. But now we're going to also have a self.hp. And we'll start this guy off at 0. We're going to just give them some default values, since we're going to want inhabitants to kind of roll their stats based on how what their base power level is or something like that. I think you'll see when we get to it. So we're not going to change how an inhabitant is initially built, but we're going to change what they have. So they have a self.hp, they have a self.armor class. What else did they say they had? A strength, self.strength. And maybe we even make these all -1, kind of indicating that they're not set. You know, that this person is so weak they're dead type thing. So we have a name, hit point, strength, armor. Okay. So we've added to what an inhabitant is here. And now what we're going to do is we're going to go ahead and add to our inhabitant the ability to roll their stats with max HP, armor class, and strength. So we'll have a def roll stats, and this guy will take in a max HP, a max armor class, and a max strength. Okay. Now, in order to use this, we're going to do some random number generation. So remember, we need to import random. We've used this guy before. And then we have something called, was it random.nextInt?
Random, I think it's randint, yeah, RANDINT.
Okay, so randint, it takes a, is there only one version? Or one version that takes the high and the low? Yeah, so you need to give it the range. So maybe we'll say the minimum you can have for anything is a 3. And then it's whatever the max value will be for it. It's going to give you your randomness, something like that. All right. So we've imported random now, so we have access to that. And then inside inhabitant, when we roll our stats, we're going to set our strength and all of those things equal to some value between 3 and whatever max HP is. Just say that's the case. So we'll say self.hp is equal to random.randint 3 to max HP. So we'll roll some random number between 3 and whatever this guy is, and that'll set this dude's hit points.
Mr. Lippman,
Yep.
would it be simpler to just equal it up to where the -1 is instead of doing the roll stats?
What do you mean? Well, but then you're hard coding it in here. You know, if you're saying
Okay.
14 or something, the reason I want to do it in roll stats, not so much that it's simpler or not simpler, it's this constructor is for generic inhabitants, where when we roll the stats for a player, we might want the stats for a player to be a little bit stronger. That's why we're having this max number, where maybe for an NPC rabbit or something like that, we might want their stats to be weaker. So we're kind of saying, go ahead and create yourself in the weakest form possible, and then we'll re-roll your stats to be something based on some information that we've provided. Something along.
Okay, so this is for the NPC or the other inhabitant?
Neither. Right now, this is just inhabitants. And then we'll use this function inside of NPCs and players to roll the stats. So
Okay.
kind of like what we were saying before, all we're doing here, we want to focus on just the little world we're inside of right now. All we're doing is we're adding an ability to an inhabitant to roll stats. We are not dictating how we're going to use that ability yet. We haven't used it yet. We're just writing this ability that, hey, if somebody were to call this function called roll stats and pass me a maximum number of hit points, armor class, and strength, it'll go ahead and reset the hit points, armor class, and strength to some random number between 3 and that value. And then we can decide how we want to use that later. All right, so whenever we call roll stats and we pass it the maximum hit points, armor class, and strength, we'll go ahead and get a, it'll overwrite our -1s with some new random values. All right, so that's for an inhabitant right now. Now let's go ahead and let's write player. So we'll say class. Actually, let's do NPC first. So we'll say class NPC. And this guy is built in terms of an inhabitant. All right, so we'll go ahead and have our constructor here. And we'll go ahead and initially just call our parents constructor, which will set the initial values for this guy, and then we'll differentiate ourselves from there. So we'll call super init, passing in our name. And that's what we had shown over here, where we called the parents constructor, passing it the value.
I don't think in its own constructor, the def in it, you don't need name then, though, right?
You do, because this had to come from somewhere. Otherwise, the example from the car thing would have been this. Now all of our NPCs are named Mike. In the example over here, all cars had 4 wheels. So that's why we hard coded it here. Where in our world that we're building with NPC. NPCs might very well have different names than each other, right?
Yeah.
So we're going to go ahead and take in a parameter for that name, and then we'll build the base inhabitant using that same name that was passed in. So understand here that this 4 that we took in here, we only chose the hard code of 4 rather than take something in as a parameter because we decided that all cars have 4 wheels in our example here. If cars could have a different number of wheels, maybe we would have taken in a parameter here for number of wheels for this car and then passed that on instead of a 4. But for this example, we decided that all cars have 4 wheels. But for our example over here, not all NPCs have a hard-coded name. They have their own name, whatever their name is. All right, so this will call upon the parents constructor, passing that name in, which will set the name equal to name. It'll initialize hit points, AC, and strength to -1, as well as current room to none. But then what we want to go ahead and do is we want to call our parents roll stats. And we're going to pass this guy, let's say the maximum number of hit points for a NPC, we're going to say are going to be 8. Maximum armor class will say 8, and strength will say 8. So they're just kind of mild, whatever. So the call to init here initializes everything this way. But then when we call roll stats, we will overwrite hit points, AC, and strength with these new values. Because we're saying that all NPCs have base stats of between 3 and 8, because we have 3 up here and 8 here that we're passing in. And that's what we will say a NPC has. Now, an inhabitant, we probably also want them to be able to display themselves. So we'll say def display. And then we'll go ahead and print out an F string. And we'll say name, self.name. And then we want to give their stats. So we might say hit points, self.hp AC self.ac and strength self.strength. And we could just say that's what it's going to print out for an inhabitant. It'll print out their name, and then it'll print out their hit points, armor class, and strength. All right, so we're going to say this for an NPC, and then we're going to go ahead and define a simple player. And we're going to say players are a little bit stronger. So we'll have class player is also based on an inhabitant. The constructor for player, we'll take it a name. We'll go ahead and call our super constructor, passing it that name and getting the initial stats all -1. And then we'll call our super roll stats. And let's say that the hit points for a player can be up to 15. And let's say armor class can be a 12 and strength can be a 10, something like that. So they're a little bit stronger than an NPC at baseline. They're a little bit tougher and they live longer, something along those lines. All right, so that's what players will look like initially.
Where does like where would we put the while loop for their health inside their own class, like for player, or is that going to be somewhere else?
Well, I would say we're not there yet. We're not trying to figure out where we're putting that. It could be in there. It could be somewhere else.
Okay.
But right now we've only created the ability to bring them into existence. They can't do anything. So we're gonna experiment with these a little bit just to see what we currently are dealing with. So I'll go ahead and leave my whole map put together here. But for this loop, I'll go ahead and just change this to false. I think that'll still run. All right, line 60. Oh, this needs to be self, comma, name. Okay, there we go. So I changed this whole thing to while false, and none of this will happen right now. So I just kind of am bypassing it just for a few minutes while we create a couple of NPCs and create a couple of players. So we'll go ahead and say NPC1 is equal to NPC. We'll call this guy NPC1. NPC2 is equal to NPC2. And then player 1 is equal to player. Call him player 1. Player 2 is equal to player 2. And then we'll go ahead and tell each of these guys to display themselves. And we should see that it's going to be unlikely that they will all be the same.
I'd still say -1 for the stats for some reason.
Let's see. No, mine shows the right thing. So you must have done something funky up here. My guess is for NPC and player, you did not call the roll stats. You need to make sure you have this piece after the constructor. So you call the constructor first, then you call roll stats for each of those. Because we see we have an NPC that has 7, 7, and 4, another NPC which has 5, 8, and 7. Then we have a player with 11, a 12, and a 4. That seems unlikely that they would be identical. Oh, they're identical because I didn't change the player I was printing out. I'm printing out player 1 twice. There we go. All right, so we're seeing some randomness now. So we have a couple of NPCs we've created. We have a couple of players we've created. They got some random values, but because of what we did inside the constructor for NPC and player, we see that pretty consistently, not that they can't be just by bad luck, but pretty consistently players are a little bit more powerful than our NPCs are right now. Okay, so now we're 4 minutes past the end of class. All right, so what we'll do is go through this code, try to understand what we're currently doing. I won't give you homework for Wednesday, or for Thursday rather, but you'll have homework over the weekend. We're going to look at writing a death match on Wednesday, or sorry, Thursday, where we have players versus monsters attack each other. All right, questions, comments, concerns, bribes? All right, I'll see everybody on Thursday.
Have a good day.
Later.